Okay, let's rock and roll. Good afternoon, everyone. I hope that we'll do a complete proof of one of the main theorems today. I apologize in advance. It's going to be quite tough. It's a lot of heavy combinatorics. Every move is very elementary, but the level of complications is quite high. That's why I decided to do it in one go, because somehow recalling details of a theorem after a week-long break, it's not a nice thing. And I really want to complete it today. But before we even go to the proof itself, I need to make one more definition. That's what I omitted at the beginning, and I think it should be among general definitions. It's definition 1.9. We say that two vertices, V1 and V2, are related if and only if there exists a path P from V1 to V2, which means that the beginning of P is V1 and the end of P is V2, or there exists a path from V2 to V1, which means that the beginning of P is V2 and the end of P is V1. So in particular, every vertex is related to itself because this vertex itself is a path from itself to itself. Okay. Now, if two vertices are not related, we call them unrelated. Okay, and I will actually most frequently use the term unrelated, but I think it's like defining connected and disconnected, right? We define what it means for a topological space to be connected, and then we say that it is disconnected if it's not connected. Okay, good. So that's the setup. I still have two elementary remarks to make concerning this new definition. So let me scroll. These are elementary remarks number 6 and 5. I edited them up. By the way, each week almost each week, I post updated lecture notes to our Moodle site. So this link is always active. And if you look for it on Monday morning, you should usually find a new version. Okay. So in the following graph, so I'm reading this elementary remark right now. Okay, let me do the highlighting.
Excuse me?
Yes?
So one vertex is not necessarily related to the same vertex?
But I just said that it is related, yes.
But I mean, is there a path from every vertex to the same vertex?
Yeah, because the vertex itself is a path of length 0.
Okay, yes. Okay, of course.
That's what I said. But by the way, I really love questions. Please ask me questions during my talk. Never, be bothered by disturbing me. This is actually quite frustrating to speak for 4 hours without seeing anybody and hearing anybody. So there are no stupid questions. Yeah. That's exactly as I said. Every vertex is related to itself because the vertex itself is a path of length 0 from itself to itself. I know it's completely trivial, but in mathematics you have to consider all admissible cases. Okay, but look at the following graph here in this remark number 6. In this graph, the vertices W1 and W2 are unrelated because there is no path from W1 to W2 or from W2 to W1. They are connected, but they are not related. And this is despite the fact that they are both related to vertex V0. So V1 is related to V0. V0 is related to W2. Sorry, W1 is related to V0. V0 is related to W2. But this is not a transitive relation. It's a reflexive relation, as we just established, but it's not transitive. And here we have that W1 is not related to W2, despite both of them being related to W0. Okay, my next elementary remark is number 7, right here. It's very much like with loops. If two vertices are related by an infinite path, they are also related by a finite path. And that's because of the way we define the beginning and the end of an infinite path, right? If some vertex is the beginning of an infinite path, then it means that there is actually a concrete vertex En for some sufficiently small number n, such that the end of this vertex is actually this vertex, which is the beginning of the path. Okay, so we can just terminate this path going to minus infinity at the end, and we can do the same on the right hand side if our path escapes to plus infinity. So very much like in this proposition 1.10 with loops, that every loop has a finite subloop. It's the same reasoning. If you have any path between two vertices, then there exists also a finite subpath of this path that relates these two vertices. Okay, so now we can go to the main theorem. So I now skip what we already did, and we begin with a proof. And this is quite a monster. It's 6 pages long. It took me several days to simplify it to 6 pages. Well, I really had big hopes that it can be done in a simpler way. When I was in Bendlevo in March this year, and I lectured about graphs, there was a number of experts on graphs, students, and one of them came up to me and told me, oh, look, I have a much faster proof. And he explained this proof to me. A few days ago, I recalled this proof, and I was very happy because I thought it would work. And when I was already typing it up, I realized that this proof, this reasoning has a fatal flaw. It actually brushed under the carpet the main difficulty of the theorem, and the proof was simply wrong. So I had to dump it and return to the old proof. However, I managed to simplify it a little bit. I added some more conceptual moves, removing some messy calculations, so I hope it will be palatable. But as I warned you already, this is a very long proof, and it's very complicated combinatorics, even though every concept I'm using is comprehensible to a 10-year-old. Okay, so without any further ado, let's start the proof. It will be done in a number of steps. And our first step is as follows. We transform our given graph E. I'm not reading the theorem again because it was already so many times on my slides, on the previous lectures. You know, the theorem is we are counting the maximum amount of paths of length k in a graph with n edges, okay? So our first step is we transform our given graph E into a graph we call E1, which still has no loops and has the same amount of edges, but with all vertices on its longest path, which we call P1. And such a path, longest path, exists because we have finitely many edges and no loops. And if you remember this reasoning around equation 1.1, we had this argument saying that if we repeat, if in a path we repeat an edge, then it means that we have to have a loop, okay? So this means that we cannot repeat edges because we have no loops by assumption, and therefore we can you must have the longest path, because there cannot be a path longer than n, because this is the amount of all edges. All right, so whatever graph we started from, it has a longest path, but remember, it's a longest path, not the longest path. There can be very many, this is non-unique, there can be very many different longest path in a given graph. That's very easy to imagine, okay? And we will see plenty of examples of it, so let me not draw a picture right now. Now, next. So we need to show that we can always do this without introducing loop or decreasing the amount of different paths of length k. Why do I have this sentence? Oh yes, yeah, we have. Yes, this is indeed what I have to show. Yes. Now, first step is completely obvious. You see, I never told you that it was a finite graph. So it has n edges, but it can have as many vertices as you want. But we are interested only in these vertices, which are endpoints, which means are in the image of a source map, or sorry, which are the start points, which means they are in the beginning of the source map, or are the endpoints of our edges. other vertices that are detached from our n edges are irrelevant for building paths. So we might as well remove them without changing the game at all. So clearly we can first remove all vertices in E0 that are not in the image of E1, that are not in S of E1 or in T of E1. They are not in the image of S and they are not in the image of T. So because this is the union of two finite sets, this way we end up with finitely many vertices, which is important in our reasoning because we will somehow do the induction on the number of indices, so we better ensure that they are finite. Okay, and now comes the first step, which is not so completely trivial, and it uses the definition which I just introduced. So furthermore, we can identify unrelated vertices. More precisely, that's not what I wanted. So more precisely, if we have a pair of unrelated vertices, then we can identify them, thus reducing the number of vertices. And because we just ensured the finiteness of the set of all vertices, there are finitely many of them, we can obviously repeat this procedure until there are no unrelated vertices. Because as long as we have any two vertices that are related, well, I should say different vertices, because now that we established that every vertex is related to itself, well, of course, we cannot remove all vertices, right? I mean, this identification doesn't change anything. But so here, what I mean really, if there is a pair of two different unrelated vertices, then we can identify them, right? And as there are finitely many vertices, when we repeat this procedure, there will be finally no two different vertices then simply all vertices will become related. Okay. So I cannot say that repeat the procedure until there are no unrelated vertices. We repeat the procedure until there are no different unrelated vertices. There are no pairs of two different unrelated vertices.
Excuse me,
yes?
Is this done in a unique way?
No, this is a very good question, Oscar. This is not done in a unique way. By no means. This is completely ad hoc, completely random, and you'll see it in an example. But what is really important for us is that there is a way. But it's by no means unique. It's like with a choice of a longest path. It's completely arbitrary. A longest path exists, and we choose it, and then we use it as a reference frame. It's kind of like choice of a reference frame. This is your time zone, and this is how you measure your time with respect to a given time zone. You measure everything with respect to a given longest path, and then when you do this procedure of identifying a pair of two different unrelated vertices into one vertex, then it's absolutely arbitrary. You'll see it very soon. But this was a very good question. Okay, and we need to introduce some names. So we call the thus obtained graph E1. But now what we have to do, we have to prove that indeed we keep our promise and we don't introduce loops and don't decrease the amount of all different paths of length k. Now, in all the algorithms I'm going to use, by design, by definition, there will be no loss of any edges. So this is why I will not repeat over and over again that we still have the same amount of edges. I will use plenty of algorithms, I will iterate them, but all these algorithms will not change the total number of all edges. So I will not repeat it. Actually, I should do the same with loops. It's also quite clear, except maybe for the first lemma. that indeed the procedure, except for the first lemma, all other algorithms in an obvious way do not introduce a loop. Okay, so now this is this lemma. It says that the graph E1 is a graph with n edges, no loops, and all vertices on its longest path. And that's exactly as in the diagram below. Okay. So I have a longest path of length L. I label its edges E1, E2 through some intermediate EJ to EL. And what is very important, and these are the troublemakers, if you want, that we admit, I like to call them jumping edges. We admit edges that omit some vertices on the way. For instance, this edge does not end, it begins at S of E1, but doesn't end at T of E1, like for instance, these two edges. It ends at T of EJ, much further. And these are precisely these edges which make the combinatorics so difficult. And the name of the game is to make moves algorithms that somehow reallocate these jumping edges in such a way that we preserve what we want to preserve. We do not decrease the number of all different paths of length k. We don't introduce a loop. And of course, we don't lose any edges. And then we make these moves, and somehow at the end of the day, we remove these jumping edges. Okay, and of course, this is the crucial part of the whole reasoning. We must see that this new graph E1, into which we transformed our given graph E, that it has at least as many different paths of length k as E. So this is what we're going to prove in this lemma. Okay. Actually, pretty straightforward reasoning, but somehow I liked putting it as a lemma. Why can't I highlight it? What's wrong? If identifying two different vertices introduces a loop, then these vertices are related. Why? Because, well, if I have a loop and a vertex on this loop, then obviously there is a non-zero length path from this vertex to itself. So when I split the loop at this very vertex, the path remains, but it no longer will be the path from the same vertex to the same vertex. It will be a path between these two vertices, right? So if identifying two vertices introduces a loop, then these two vertices are related. This is very important. So therefore, we can draw an important conclusion that identifying two unrelated vertices cannot introduce a loop. So E1 is a graph without loops. This is a very important statement. Next. That's an obvious remark that E1 has, again, n edges because we do not identify the edges while identifying unrelated vertices. Remember, what we do, we just identify vertices, but we drag along all the edges. No edge, no pair of edges gets identified in the process, right? This is just identifying vertices, not identifying the edges. So the number of edges remains constant, it's n. And moreover, as identifying vertices can only increase the number of paths, right? Because when can you lose a path in your graph? When you cut at a certain vertex. You detach edges that are attached at a certain vertex. But when you're identifying vertices, you only introduce new possibilities. Remember that a path is given by an equality. The endpoint of one edge is the beginning of the other edge. So if we just make more identifications, we add more equalities. We do not invalidate all qualities, right? So that's why introducing, making such identifications cannot decrease the number of paths of E1. It can only increase it. So the crucial property of all algorithms we're going to construct and apply is here clearly satisfied. Is going to be much tougher for other algorithms. And now I just have to argue that all these vertices that we have are actually on the longest path, on a longest path. And that's a certain reasoning by contradiction. So we suppose the contrary, right? We suppose the contrary. We suppose that any two vertices are related, any two different vertices are related, but there is a vertex V that is not on the path P1. Now I say the path P1 because I already chose it. So this leads to this picture, okay? I have my longest path P1 with edges E1, E2, intermediate EJ up to EL. But I assume that there is some fugitive vertex V that doesn't want to stay on the longest path. But I will show that it leads to a contradiction, that such a vertex V cannot exist. So how do we arrive at the contradiction? So first observation is the following. When you look at the path Q0, which joins S of E1 with V, that it must go from S of E1 to V, as otherwise P1 would not be well, it should be a longest path, right? Because if this vertex Q0, sorry, path Q0, it's not these are not edges, these are paths. These Qs are paths, not edges. So if this path Q0, if it were from V to S of E1, well, then we could compose it with this path P1, and we would get a path which is strictly longer than P1, which contradicts the maximality, the maximal length of a path P1. Okay, so Q0, which makes this vertex S of E1 and V related, must be a path which goes from the beginning of E1 to V. All right. Next. This highlighting is not so easy, but I hope this is the last day I'm doing it from home. And for such a complicated proof, I think it's still easier than writing on the blackboard, especially as there are many, many long sentences in English. So furthermore, the fact that P1 is of maximal length and the fact that there is no loop in our graph E1 forces adjacent paths to have the same orientation, right? We established with our procedure of identifying vertices cannot introduce a loop because we identify only unrelated vertices. And for starters, to begin with, we have no loops. So we have no loops and we have a procedure that cannot introduce a loop. So we have no loops, right? Now, why is the case? Because if you look at any adjacent vertices, paths like here, take a path Qj minus 1 going from the beginning of Ej to V, and then look at the path Qj going from the end of Ej to V. Well, if they had opposite, if Qj had an opposite orientation than Qj minus 1, sorry, which way this should be? No, if Qj minus 1 had the opposite orientation than Qj, then we would have a loop, right? Because then we would go Ej, Qj, and we'll go back by Qj minus 1.
But I think another argument could be that we could construct a longer path because
yes.
from
yeah, but this is why I said I used two facts that this is maximal. So if I have that Qj minus 1 it goes the other way around, then it does in the picture, then we have a loop. If it is Qj that goes back from V to the end of Ej, then we contradict the maximality, because then we have a path which goes from E1 to Ej, but then instead of taking a one edge step Ej, we go by the path Qj minus 1, and return to the endpoint of Ej by Qj. And this is strictly, this subpath is strictly longer than 1 because paths Qj minus 1 and Qj have at least one edge. So we can, when we jump this edge Ej, we use at least 2 other edges. So this strictly increases the length. So it yields a path which is at least by 1 longer than a longest path P1, which is impossible by the maximality. You see, that's why I said that by the fact that P1 is the maximal length and we have no loops. So we use the maximality of P1 to reject the situation in which Qj goes in the opposite direction. And we use the fact that we have no loops to reject the possibility that Qj minus 1 goes in the opposite direction. So they are all outwardly oriented. All these paths Q must go from a vertex on a longest path to V. Okay, so and this is exactly what I said here. Right, hence all these paths like Q0 must end in V, and they start somewhere on a path, on the path P1. But this yields the desired contradiction, because when we look at the path QL and the fact that this is forced to point outwards, oh, I really don't like this highlighting. It contradicts the maximality of a length of path P1. Right, because then we have a strictly longer path, E1, EJ to EL, but when we follow it by QL to V, and this is a path which is longer than P1, which is impossible. So whichever way we play it, it's a contradiction, so such a fugitive vertex V cannot exist.
Could I have a question?
Sure.
So what would happen if QL have the opposite direction? Because if we look on SEL, EL, so we could have increased a path only for 1.
Yeah, but that's enough. Look, that's the same argument as before.
No. From SEL to TEL is 1. And
yes. And then, going
never
by
mind.
QL minus
Yes,
1 and QL is 2.
Is everything okay?
Yeah.
Sorry.
It's the same argument as for EJ. It's exactly the same.
Yes.
Yeah, we just proved that first Q0 must be pointing outward, when we prove that actually all other paths must be pointing to V. And at the end of the day, we just get a contradiction with QL. Okay. Okay, great. So we are done with the lemma, and let me show you this picture one more time. So remember, now our graphs look like this. We have a longest path, not the longest, a longest path. We choose it, we name its edges, and this is our frame of reference. When you measure distance, you measure it from some point. When you measure speed, you measure it relative to some frame of reference. And the choice is completely arbitrary, but we can make it, we label it, and we use it. But you should remember that now all our graphs we consider look like this. And we have two, yeah?
And this algorithm, we do this algorithm to obtain that all vertices are in the path P1, yes?
Yeah, I mean,
in the way that all vertices.
All our further algorithms will revolve around our fixed and chosen path P1. But we have two hurdles to overcome. One, the combinatorics is made unhandleable, untangible when we have jumping edges. So we have to do something to remove. Well, we cannot remove the edges because we cannot reduce the number of edges, but we have to reattach them in such a way that they are no jumping anymore. And another thing is that we want to have L equal to K. We want to have our longest path to be of length K to have the right combinatorics. So these are two things that we are looking at. We want to shorten a longest path to length k, and we want to remove jumping edges. But that's easy to say, more difficult to do. But we'll do it. That's what we have the remaining 2.5 hours for. Okay. Let me scroll to the end of this lemma, because lemma is done. And let me make a couple of preliminary cleaning. So we can make some further assumptions without losing the generality. These are just, if you want, technical assumptions so that we have enough room for our constructions. If we get to cases that are too trivial, things follow immediately, and we don't have to be concerned with these cases, but we have to somehow separate them out and check that, tick the box that they work, say why they work, and then make further assumptions without the loss of generality. So first, we can assume that the length of P1 is at least k, as otherwise there are no paths of length k. If a longest path is of length smaller than k, then there are no paths of length k whatsoever, 0. We are not interested in such graphs. Obviously, such graph having 0 paths of length k will not maximize. 0 is always less than any natural number, and we obviously have graphs with at least one path of length k, because we can align all the edges into one long path using an edges. So obviously we have graphs that have at least one path of length k. So we can completely dump the graphs which don't have any paths of length k. All right, so without the loss of generality, we can assume that L is greater or equal to k. But it gets even better. Furthermore, if we are in a situation when L is equal to k, then the edges that begin and end not in consecutive vertices, I call them jumping edges, they do not contribute to paths of length k, right? Because they make a shortcut. They jump over an edge. Sorry, they jump over a vertex. So it means that they're in a path which has fewer than k plus 1 vertices, which means this is a path shorter than k. So such edges do not contribute to construction of paths of length k. So we can reattach them without losing any paths of length k. And we can reattach them in such a way that they begin and end in consecutive vertices. So then the situation is very easy, and we already get a graph of a desired form, which we will, after a lot of hassle, will get at the end of the proof of a theorem. Right? So if L is equal to k, our story is quite simple. We almost immediately get what we want, and then we just have to apply the final optimal distribution algorithms, which is elementary combinatorics, along the lines of the problem which Jacek solved at the recitation classes. The even distribution of most optimal even distribution of edges among vertices leads to the biggest amount of paths of fixed length. Okay. Next. Yeah. Yeah, it's this is somehow continuing what I already said. This is summarized here in this sentence, right? That such a reattachment of vertices, of edges, so that they begin and end at consecutive vertices. Obviously, it does not introduce any loops. In order to introduce a loop, we would have to attach the beginning of an edge at or after the end of this edge, and we are not going to do it. It's sufficient when we attach the beginning of an edge to one vertex earlier than the end of this edge. Then we introduce no loops, okay? And we get rid of all jumping. We eliminate all edges that jump vertices, okay? So without the loss of generality, we can assume not only that L is greater or equal to k, we can actually assume that L is greater than k. Maybe I will show you this final step when after a lot of work, we arrive at a path of this form. So we have a path, a longest path, which is of length k. And you can see that there are many different paths, because if I have B1 edges from the first to the second vertex, I have B2 edges from the second to the third vertex, and so on and so forth. Obviously, I have plethora of different paths of length k. And I just choose and label one of them for reference purposes. But observe that if I have L equal to k, I can immediately get into this situation. And then the only thing which remains to be done is this optimal redistribution of edges to get the maximal amount of paths, right? But if L is bigger than k, we have to go through a number of pages to get to this situation. Okay, what else can we assume? There's another well, obvious assumption we can make without the loss of generality. And I'm telling you, this is just to give room to our construction. Otherwise, the situation becomes too trivial, and what we construct does not exist. So finally, we can forget about the case k equals to 1, because then we're immediately done. For k equal to 1, it's obvious that the number of all paths of length 1 is just n, because these are just all the edges. And if you look into our formula for Pnk, when we plug in k equal to 1, we obviously get n. Okay, so we can assume that k is greater or equal to 2. Yeah, look at this formula. When n is equal to 1, then obviously r is equal to 0. Lowercase n is equal to capital N, and then we have n plus 1 to the power 0. It vanishes. I have capital N to the power. I have a capital N to the power 1 minus 0, which is capital N. So all checks. Okay, so we just cleaned our field a little bit. Yeah, we assume that L is strictly bigger than K. We assume that K is strictly bigger than 1. And now we have enough room to work with. Okay, let's make another step. When we have a jumping edge which starts at the first vertex, we can actually reassign it without much hassle. So look, if we have an edge starting at the first vertex, but ending not in the second vertex, then we shift the beginning of such an edge to S of EI. So I assume that I have an edge which starts at the first vertex, but it ends at the end of the ith vertex, and I is bigger than 1. Okay, so then I shift the beginning of such an edge to the beginning of EI. Right, and then this becomes an edge from S of EI to T of EI, and obviously it does not jump over any vertex. Clearly, we do not introduce a loop when we do this, right? Because remember, to introduce a loop, we would have to put the beginning of our edge at its end or further down along this path. And if we don't do it, we don't introduce a loop. And also, as there are no edges ending in S of E1, because this is the first vertex, we do not lose any paths this way. Right, because if we have a jumping edge starting at the first vertex, if we move the beginning of the jumping somewhere, we have not lost any path, because this jumping edge, if it is part of any path, it is the first edge of any path. So by shifting its beginning farther down, we have not lost this path. This path now looks differently. It begins somewhere else, but it still exists. We have not deleted it. Okay. So we do not decrease the number of all paths of length k. We do not introduce the loop, and we do not decrease the number of edges. And we call the thus obtained graph E2. And this is how it looks like. Now remember, this is just a picture. The only thing which is real in this picture is a longest path P1. I really mean it. I have these edges E1, E2, E3 up to EL. But whether I have here two additional edges from S of E1 to S of E2 or 1 billion additional edges, I don't care. I think that it's more convincing to draw an example of a graph than some generic picture which would be drowned in generic notation. Just so that we're on the same page and understand each other. The only thing which is literally meant on this picture is the longest path. Everything else is just an example. For instance, I'm not saying that the only edge from S of EL to T of EL is the edge EL. There can be many others. There can be some jumping vertices, edges that end at T of EL, whatever. Okay, but we already made some progress. We removed jumping edges from S of E1. There are no jumping edges beginning at S of E1. And somehow what we want to do, we want to iterate this procedure until at the end of the day, there are no jumping edges. But this is not so simple. This is actually the place at which what I thought was a simpler proof, which I was told by a student in mid-level, went wrong. Okay, so if we want to continue this procedure, well, we must be a bit smarter. We must enrich our algorithm. Otherwise, it will not work for the simple fact that now, say, look at this jumping edge over here, okay? If I shift the beginning of this jumping edge from S of E2 to S of E3, I'm losing some paths. I'm losing paths that, for instance, were given by an edge going from S of E1 to T of E2, and then they're continued by this jumping edge. Now, this is no longer a path because I shifted the beginning of the jumping edge, so I lose some paths. So I have to do a little bit more in my algorithm not to lose any paths of length k. Well, that's why we do it in some steps. So our first step, well, it is almost exactly as before. Oh, this highlighting is really quite a nightmare. We transform E2 to a graph we call E3 by shifting the beginnings of edges from S of E2 to T of EJ, where J is bigger than 2. We shift these beginnings to S of E3. So like in this case, we shift the beginning of this jumping edge from S of E2 to S of E3. So it still might be a jumping edge. I mean, here this jumping edge ends at T of E3, but it can end, say, at T of E million, right? Then just shifting the beginning of this jumping edge by 1 would not make it a non-jumping edge. It still could be a jumping edge, but we don't care. We just want to remove jumping edges starting at given vertices, and we go from the left, okay? So then we get a graph which looks like here. We have no jumping edges starting at S of E1, and also we have no jumping edges starting at S of E2. But we lost some paths, so we have to do one more move. And how do we do it? Well, so as I said, this time we lose the paths of length k that started in S of E1 and involved the just shifted edges. And these paths are lost because we cut these paths. But now what do we gain? Well, we gain the paths of length k that start at S of E2 and then involve the shifted edges, right? Because a shifted edge started as S of E2. Now it starts as S of E3. So I can use any edge from S of E2 to S of E3 to connect to any path which starts with a jumping edge. So these are the new paths that we gained. right? These are really new paths that we gained that weren't there before because the shifted edges were not starting at this vertex before. Okay, so we gain and we lose. But we have to make sure that we gain at least as much as we lose. And to this end, we need to make one more move. Let me first introduce some notation. So let AI let AI denote the number of edges starting at the vertex S of EI. Okay. So that's first part of notation. And now let me denote by X the number of all different paths of length k minus 1, which has a shifted edge as its first edge. And you see already here we use that k is at least 2. Because if k were 1, then we would talk about paths of length 0. And well, I mean, we can still do it, but these assumptions on k and l are actually useful. Right, so this is just the notation. AI denotes the number of edges starting at S of EI, and X here we choose a shifted edge. We can do it for any shifted edge, but let's focus attention. There is at least one shifted edge, otherwise we are done. Right, if there is no shifted edge, not jumping edge starting at S of E2, then we don't have to do this procedure. Right, then we can move forward to the next step. But this is just to show you what happens if already at S of E2 we have a jumping edge. Logically speaking, what I'm doing right now is not necessary because we will do it at the generic place later on to have like an induction step. The way we are proceeding is that this first step, creating E1, was like the first step of an induction, and we can do it in an obvious manner. This is easy to explain. And now I want to show that I can somehow iterate this procedure of removing jumping edges starting at further vertices. So I have to prove that I can make an induction step. So what is most important is the reasoning at some generic place M. But I think it's good to explain it for starters in case this M is equal to 2, that we really already have a jumping edge starting at S of E2, and how does the procedure play out when we want to shift it. Okay, so we assume that there exists such a shifted edge. Otherwise, we are in the further stage of the proof, which we handle later on. Okay, and so we choose such a shifted edge, and we make this notation. Remember, X is the number of all different paths of length k minus 1 that have this shifted edge, say this one, as the first edge of this path, right? So what's this additional move that we make? So as I told you, to ensure that we gain at least as much as we lose, if it so happens, as it is on the picture, that the number of edges emitted from S of E1, which is denoted by 1, is bigger than the number of edges emitted by S of E2, which is denoted by A2, then we swap the edges in the following way. Yeah? We switch places of the edges from SE1 to T of E1 with the edges from S of E2 to T of E2. And you can see it on this picture. So we take this part of a graph and swap it with that part of a graph. So now our longest path begins with an edge E2. Of course, when we just relabel it and then we still call it E1, E2, and so on. But here the point is that we make this switch. You can also think that you keep E1 and E2 unchanged, but you shift the edges in such a way that we have the number of edges from the first vertex to the second vertex as big as there was a number of edges from the second to the third vertex, and then the other way around, you make the number of edges from the second to the third vertex as it was from the first to the second, right? So you make the swap so that somehow the idea is that you increase the number of edges emitted from consecutive vertices. If you go to the right with vertices, you should well, maybe not increase, but you should not decrease the number of emitted edges. Okay, so that's this additional move that you make. And look, so this saves the day. Because of the following reason. So as the number of different paths of length k beginning with a shifted edge is unchanged, right? In this move, we don't change this number of paths involving a shifted edge. Just that we change the beginning of a path, we don't delete it, right? So this number is the same. Then when you look at the number of different paths of length k with a shifted edge, the same shifted edge as the second edge, well, this amount is not a decrease. It's not decreased because before, if we had a path of length k which had a shifted edge as the second edge, then the preceding edge was one of these A1 edges going from S of E1 to T of E1. And now, because we make sure, but I think I have a feeling that I skipped something. Oh yes, yeah. I skipped the sentence. So sorry. I somehow forgot to highlight it. And it's good to have this mental picture in mind when you read the subsequent sentences, right? So we introduce this notation for x, and look, if a shifted edge is the first edge of x different paths of length k minus 1, then we lose a1 times x many paths of length k, right? But we gain a2 times x paths of length k. That's clear because when we take, if you want, all paths of length k containing the shifted edge or a shifted edge as the second edge, well, then we have one preceding edge, and then we are looking at all paths of length k minus 1 that start with our shifted edge. And this number is unchanged when we make our move. What is changed is the number of edges that can precede our chosen shifted edge. And before the move, we have a1, many edges that can connect to a path with the path of length k minus 1 starting with the edge, with a shifted edge. And in the second case, we have a2 of such preceding edges. So here the number of all such paths of length k having the shifted edge as the second edge is a1x, and here's a2x. Okay, so we have to make sure that we are. Then we have a problem if a1 is bigger than a2, because we lose more than we gain. This is why we make this swap. We exchange places between a1 and a2, and when exchange places with a1 and a2, then exactly what happens is that the amount of paths we gain is a1x, and the amount of paths we lose is a1x. because we make this exchange. And this is what is spelled out in that sentence. Yeah, the number of different paths of length k, beginning with shifted edge, is unchanged. So that's here you lose nothing. When you look at the number of different paths of length k with a shifted edge as the second edge, and that's the situation we just discussed. And when we make this permutation, this rearrangement, then this is not decreased. It can be increased, because if we have that A1 is strictly bigger than A2, and then we make such a swap. Well, anyway, it's not decreased, okay? And there are no other paths in E2 involving a shifted edge. Remember that because a shifted edge starts in the third vertex, then if we are talking any other paths involving a shifted edge, then the number of such paths of length k does not decrease. Why? Because, yeah, it's really hard to see while looking at the picture. So we are concerned with paths of length k involving a shifted vertex. Okay, say that it's going to be this vertex. No, vertex, sorry. This is another problem with this lecture. It's so easy to confuse the words vertex and edge. So please forgive me whenever I do it and look at the context. It's usually obvious from the context what I should say. And I'm trying very hard, but every now and then I just confuse these two words, edge, and the vertex. Okay, so I'm looking at all paths of length k that involve a shifted edge. Okay. Now, if these are paths of length k that start at this edge, then this is clearly unchanged by our moves. These two moves that we make do not affect at all the number of different paths of length k having the shifted edge as the first edge of the path. Okay. Now, when we look at this edge as the second edge in such a path of length k, then this is the reasoning which we just went through. We by making this swap between A1 and A2, we gain more than we lose. So we are good when you have paths of length k having the shifted edge as the second edge. Well, what happens is that, well, actually, sorry, here this wait, we gain, yeah, because by making this swap, we have actually the same number of paths of length k having the shifted vertex as the second, the shifted edge as the second edge in the path. It's just that sort of the beginning of this path is shifted by one, but we do not lose these paths. So it's actually the same amount. And now when we look at all paths of length k having the shifted edge as the third edge, and it cannot be the fourth edge because it's too early in the graph. It begins at the third vertex, so it can be only the third. It can be the first, the second, or the third edge of any path of length k, because there are no paths starting earlier than the first edge, the first vertex. Okay, so when we look at all of them, then this swap does not change the number. We still have the same number of paths of length k minus 2, and here we use that k is at least 2. We have the same number of paths of length k minus 2. If k is equal to 2, we're talking paths of length 0. That's still okay. There is one such path. It's a given vertex, the third vertex. This number is unchanged by our procedure. And now when we look at all paths of length 2 that connect the first vertex to the third vertex, then all this rearrangement procedure doesn't change because the multiplication of two numbers is the same. A1 times A2 is A2 times A1. Okay, so that's somehow on the picture we explain that what's written here. That the number of different paths of length k involving a shifted edge is not decreased. Okay. So now what we have to make sure of is that transforming our graph from E2 to E4, we did not decrease the number of all paths of length k not involving the shifted edges, right? But then the situation is actually simpler, because when we look at paths that do not involve the shifted edges, then we can simply just remove the shifted edges from the graph and see what happens by our move. And our move is simply the following. If A1 is strictly bigger than A2, then we have this permutation, then we have this exchange of vertices and edges that we discussed earlier, right? That's the only change that we make. And it does not, for much the same reason as before, it does not change, does not decrease the number of paths of length k. But let's go through this argument in detail. It's actually just one sentence because that's pretty clear what's going on. So let me highlight it, as this is what we discussed. Remember that we already explained that without the loss of generality, we can take k greater or equal than 2. Then when you take any path of length k in E2 that does not involve any shifted edge and that starts from S of E1, of course, it must involve an edge from S of E1 to T of E1, and it also must involve an edge from S of E2 to T of E2. There is no other way. There are no jumping edges between these three vertices. And since the path is of length at least 2, well, we must go from S of E1 to T of E1, and from T of E1, which is S of E2, to T of E2. There is no other way. We can go further if k is bigger than 2, but we definitely must step on these 2 steps. Okay. And if we go further, then what do we do? How many different paths we have? Well, we just look at all different paths of length k minus 2 emitted from S of E3, and we multiplied by A1 times A2, and that's exactly what is written here. Right? We denote by Y the number of all paths of length k minus 2, of course, not involving any shifted edge and starting at S of E3. And then we see that before we move, the amount of all such paths was A1 times A2 times Y, and after we make the switch, the amount of all such paths is A2 times A1 times Y. But the multiplication of natural number is commutative, so we do not change the number of such paths, right? And note that in case k equal 2, we just have y equal 1 because there is only one path of length 0, which is a vertex, right? A path of length 0 starting at S of E3 is S of E3 itself, and there's one such path, so y does not figure in this combinatorics. So that's just an obvious special case, which for the sanity check we should consider, but it's obvious what's happening here. But now we should consider the situation where we look at paths not involving any shifted edge, but which does not necessarily start at the first vertex. So concerning all paths of length k, starting at the second vertex from the left and non-involving any shifted edge. So here the number was the same of all such paths. But now here I claim that we do not decrease the number of all such paths when moving from E2 to E4, because we have at least as many edges going from the second to the third vertex and exactly as many paths not involving any shifted edge and starting at the third vertex. So we might increase this number if indeed A1 was strictly bigger than A2, and then we made the switch. But we definitely don't decrease it. And finally, when we look at the number of all paths of length k not involving any shifted edge and starting at the third or further vertex, it is unaffected by our procedure of going from E2 to E4. Remember, when you don't involve a shifted edge, you just remove all these shifted edges from the picture, and then this procedure of going from E2 to E4 is either nothing or it's the permutation of the first two batches of edges. But when we consider things that start at the third vertex or further, this procedure does not affect any paths. So in particular, it does not affect the number of all different paths of length k starting at S of E3 or further. Okay, so now I guess we are done with this reasoning. I took you to the graph E4, and I hope that I convinced you that we have not lost any paths of length k. We have at least as many paths of length k as we had. Obviously, we didn't lose any edges, and we did not introduce any loops. Okay, so if you want, this is the situation as on this picture. Okay, we have no jumping edges from starting at the first vertex or at the second vertex, and the rest is possibly still a mess. However, to iterate the algorithm, we have to do one more step, because it might happen, as it happens here at this picture, that simply by the very nature of a graph, and it already could have happened for us at S of E2, right? It could have happened that there is no jumping edge starting at S of E2. Then we would introduce this procedure that I'm going to describe right now already back then. Okay, so if we have a jumping edge starting of S of E2, this is our first move. If we don't, then our first move is what I'm describing to you right now. But if there is a jumping edge starting of S of E2, and then we move to the further situation, then it can happen that also S of E3 does not emit a jumping edge. It might also happen that S of E4 also does not emit any jumping edge. And we have to look at such a situation and make one more ordering move in order to proceed with our algorithm. So that's what this paragraph is about. I'll just start now highlighting paragraphs, because doing it by sentences is a nightmare. So now we take our graph E4 and we choose a natural number n, which is at least 2 and at most k, and we choose it to be the biggest number such that for all i's less or equal to m, all edges emitted from S of EI end in S of EI plus 1. Right, so even if we do our procedure of moving, jumping, we can do our procedure of moving jumping edges further down, so that we have another vertex which does not emit the jumping edge. It might happen that the following vertices by themselves have no jumping edges. So there is no need to shift anything from these vertices, because there are no jumping edges starting at these vertices. But now we are getting into a situation where we do not have a non-decreasing number, non-decreasing sequence of numbers denoting the amount of edges emitted from a given vertex, right? So what we do, we take this set of m elements, 1, 2, up to m, and we choose a permutation, sigma, of this set, which has the following property, that the number of all edges emitted from S of E sigma 1 is less or equal than the number of all edges emitted from S of E sigma 2, and so on and so forth. And then the biggest one is the number of vertices emitted from S of E sigma m. Such a permutation obviously exists because if I have finitely many finite numbers, I can always order them from the smallest to the biggest. I think this is completely clear. There's no need to justify it, right? Such a permutation always exists. I have a finite amount of finite numbers, and I just order them from the smallest to the biggest. I can always do it. It's of course non-unique because I can have a bunch of numbers on the way that are just equal. I'm not saying that all these numbers are different. Remember, these are non-sharp inequalities. But I can surely choose, non-uniquely, but I can choose such a sigma that all these inequalities are satisfied. And then I rearrange my graph according to this permutation. I arrange it in such a way that the first vertex is S of E sigma 1, and all edges it emits end in S of E sigma 2. Then the second vertex is S of E sigma 2, and all edges it emits end in S E sigma 3, and so on, until the nth vertex being S of E sigma m, and emitting edges ending at S. There should be, sorry, there should be, no, and ending at em plus 1, right? There is no further permutation here, right? I just do not change my vertex S of em plus 1. Right, so this way, by construction, when I choose when I choose my notation to be for because you see, writing all this S inverse of S of E sigma 1 and so on is a little bit awkward, right? I'm just calling this number A1, the second number A2, and the nth number AM. And by construction, these numbers satisfy the inequalities A1 less or equal than A2, and so on and so forth, until less or equal to AM. Okay, and these numbers, I repeat, signify the number of edges emitted from a given vertex. So this is the situation at which we get. And now look, by the very construction here, there must be a jumping edge. Okay. Well, sorry, not quite. Not quite. It can happen that m is equal to k, and L is equal to k plus 1, and then there is no jumping edge. But then we are done. This is a special case which I discuss later on. But anyway, if L is strictly bigger than k plus 1, then we must have a jumping edge. That's by definition. Okay, let me finish this reasoning. We should have a break in 15 minutes. Okay, I'm trying to think about what I just said, and I'm wondering here if I should really allow m being equal to k. Okay, let me get back to it later. Well, obviously, when I look at the graph Fm, which I just constructed, it has no loops. This is just a rearrangement procedure, so this introduces absolutely no loops. Moreover, the number of all paths of any given length starting at this vertex S of em plus 1 or further down is the same in Fm as it is in E4, because this part of the graph is completely unaffected by this move. And the number of all paths of length k starting at the first vertex is the same as in Fm. In Fm as it is in E4. Why? Because if I have because m is less or equal than k, then any path of length k that starts as the first vertex must involve edges in between all pairs of consecutive vertices. Right? We cannot skip any step. When you go by a path from the first vertex, and the path is of length k, and m is at most k, well, then you are taking a path which goes along these lines. And the amount, so when you look at the amount of all paths of length k starting from the first vertex, then this is amount of all paths of length k minus m starting at S em plus 1, and this is unaffected by our move. This is the same in E4 as it is in Fm. This number does not change, times the multiplication of all these numbers. And of course, when we do a rearrangement, multiplication is commutative, so such a permutation does not affect the number. Yeah, because this is the number of all paths of length m that start at S of E1 and end at S of Em plus 1. And this number is unaffected by this permutation. So here the amount of such paths is exactly the same. And now when we look at paths that start somewhere in between at the second vertex, the third vertex, or this is m at the nth vertex, okay, then, well, we do not decrease the number of all paths of length k, because we take paths of length k minus the number of edges we take from here, and this is unchanged. Find the multiplication by all these numbers which come from a chosen intermediate vertex till the last vertex. But remember, our permutation orders these numbers from the smallest to the biggest. So because you are truncating the beginning of your product, you are truncating the smallest numbers. So this means that when you take this permutation sigma, you are possibly increasing this product, but you cannot decrease it. If you have a bunch of numbers that we multiplied, and you replace in each and every of these numbers, but number which is at least as big as this number. So of course the product will be at least as big as the product that it was before. And then you multiply it by the number of all paths of appropriate length starting at S of Em plus 1, which is unchanged by this procedure, and voila, here you go. You did not decrease the number of different paths of length k when moving from E4 to Fm. And now I want to discuss the situation in which m is equal to k. Well, in a way, when m is equal to k, then we don't have, yeah, so somehow this this definition was not quite precise. Yeah, I have to correct it in the notes. So we define m as the biggest number such that for all i's less than m, no, wait a second. No, sorry, the definition is correct. Sorry. If m, look, if m is strictly less than k, right? Then because it's the biggest number with this property that there are no jumping edges for all, there are no jumping edges beginning at m or earlier, right? Since this is the biggest such a number, then if m is strictly bigger than k, it means that if you look at m plus 1, that at the m plus first vertex, there must be a jumping edge. That's just by the definition, okay? So here this picture is created for m strictly less than k. And then we must have a jumping edge starting at s of en plus 1. This is what was bothering me. But if m is already equal to k, well, then we are done. We don't have to have a jumping edge starting at s of en plus 1, but still m is the biggest number, less or equal to k, with this property that I wrote here, that for all I less than m, there are no jumping edges starting at s of ei. Sorry, so the definition is correct. It's just that we have a special case. If m is equal to k, and for instance, L is equal to k plus 1, then there are no jumping edges. If L is strictly bigger than k plus 1, but m is equal to k, then we don't care. There might be a jumping edge starting at s of ek plus 1 or not. It's irrelevant because m is still the biggest number with this property. The biggest number less or equal than k with this property. We have this truncation by k, right? But if, yeah, this is what was bothering me, sorry. So everything what was written was correct, but I forgot the logic of why it holds water. Yeah, so now we focus on what's in this picture. So we focus on the situation in which m is strictly less than k. Because if here m is equal to k, then we arrive at the graph at which we want to be. And we continue the procedure from then on, right? You see, at a certain moment, by applying a complicated procedure, I finally arrive at the graph fk, you see? So I iterate algorithms and I arrive at the graph fk, which is exactly defined as the graph fm, but you know that everything is as you want it to be. There are no jumping edges starting at s of e1, s of e2, up to s of ek. And that's what you want. This such a graph is called fk. And if in this previous situation, in this picture, right? If it so happens that m is already equal to k, well, then we are done. We don't have to do this complicated procedure that we must do otherwise, that is when m is strictly less than k. Okay, now this is the most difficult part of the proof, in my opinion, to handle the situation on this picture when m is strictly less than k. And I think that's the last thing we can do before the break. So now assume that m is less than k, strictly less than k, and let us continue let us continue, show that we can continue this E2 to E3 to E4 to Fn procedure until we finally obtain a graph fk. Okay? Well, indeed, assume that we have an index j, and j can be any index from 0 to m, with the property that aj, oh, sorry, I should highlight. With the property that aj is less or equal to am plus 1, and a plus 1 is less than equal to aj plus 1 for some of these j's. Now, when I say j equals 0, then what does it mean to have a0? Such a number does not exist. Well, it's just a question of notation. We say that a0 is equal to 0. And any positive number is strictly bigger than 0, and all these numbers from a1 to and further are positive. So then this inequality is void. And we are just basically saying that when j is equal to 0, then we are simply saying that am plus 1 is less than equal than a1. And this is a meaningful inequality. It can happen. In the other extreme, we are simply, when j is equal to m, well, we are simply saying that am plus 1 is bigger even than am, and this inequality is trivial because am plus 1 is obviously less than equal to am plus 1. So it might happen that we have this sequence of non-increasing positive natural numbers, and then we take another positive natural number, but it happens to be bigger than all of them, or less or equal than all of them. So then we are done. We don't have to do any permutation. But if it so happens that I can squeeze it in between, I have a generic situation, but I can squeeze in this am plus 1 in between aj and aj plus 1, then I must do a certain cyclic permutation, which is described here. If we are in a situation like this, then we move to the m plus second vertex, the beginning of any edge, starting at the m plus first vertex and ending at the m plus third vertex or further. Okay, we move to the m plus second vertex at the beginning of any edge, starting at the m plus first vertex and ending at the m plus third vertex and or further. So we implement. Sorry, I'm confused here. We move to. I don't understand this sentence. We move to where are we? Ah, yes. So yes. Okay. So m is strictly less than k, and somehow again what I'm missing is that k is at least that L is at least k plus 2. Sorry about this, but I told you this is a complicated proof. Well, we might also be in a situation when m is really strictly less than k. No, sorry, no, we are good, because you see, m is strictly less than k, and L is strictly bigger than k. All right. So it means that the difference between L and m is at least 2. Okay. So this means that we have m plus first edge in our longest path, and we have m plus second edge, right? Because k is at the earliest here, and L is at the earliest there. So this means that we must have a jumping edge. Okay, everything works. But I got puzzled for a while. Okay. So by the definition of Fm, right? Because it's the biggest number such that blah, blah, blah. We know that in this situation, when m is strictly less than k, and I already argued earlier that L is strictly bigger than k, we must have a jumping edge. Because here, we have definitely edge em plus 1, and we definitely have edge em plus 2. Because L is at least m plus 2. It cannot be any smaller. Right? And then we must have a jumping edge. And when we take any of such jumping edges and we move the beginning of this jumping edge from S of em plus 1 to S of em plus 2. So this is what's in the sentence. When we move to the m plus second vertex, which is here, right? The beginning of any edge starting at m plus 1, so a jumping edge, and ending at m3 or further. So we shift the beginning of any jumping edge starting at this vertex to vertex m plus 2. Okay, everything makes sense. And next, we implement the swap of edges according to the recipe. This is the cyclic permutation I told you about. m plus 1 goes to j plus 1, j plus 1 goes to j plus 2, and so on and so forth until m goes to m plus 1. And this allows us to, what? I can now remove the highlighting and go to the next page. And this is the picture that we obtain. Okay, so this is the cyclic permutation that we made. We simply observed that am plus 1 as a number is between aj and aj plus 1. And what we did, we made the cyclic permutation. Here we used to have this am plus 1 many edges. Okay, so what we did, we shifted all these edges to be in between aj and aj plus 1. And then everything else we pushed further. So it's like a cyclic permutation, but involving only these edges starting at s ej plus 1 or further. Okay, I hope you see this cyclic permutation, and the rest is unaffected. And we pick it up after the break. I just now pause the recording. I don't stop it. I have to figure out how to do it. And then I resume the recording, then resume the lecture at 2 p.m. And mind you, I'm not killing this session. This will be all the time this lecture session. Today, there is no recitation class session. So you can just remain tuned. And we get back to the lecture at 2 p.m. sharp. Okay, see you then. Okay, welcome back, everyone. For starters, do you have any questions? We are now at the situation at the top of page 10. We arrived at this graph, and now I want to convince you that we did not lose, it did not decrease the amount of paths of length k. But do you have any questions concerning as to what's going on? Is everything clear? Well, nobody's protesting, so I assume it's okay. That's the most difficult part of the proof, most complicated, but we are almost done. So recall what happened. We argued that why can I go back? Okay. We argued that if m is less than k, then yes. Any question? I just heard some sound, so I'm asking. Anyway, so we argued that in this situation when m is strictly less than k, we must have a jumping edge, okay? And then we shift the beginnings of all such jumping edges by one step. And then we make a cyclic permutation procedure, which is described here. Okay, so this way we arrive at this graph. Now we have no jumping edges up to here, up to this vertex. Now this is, from then on, we don't control what happens. There might be a jumping edge here, or there might not be a jumping edge here. I don't care. What I care about is that for all these vertices from 1 till m plus 1, but here there are no jumping edges that start at these vertices. Okay, that's important. This is what we did by construction. But then there is also the cyclic permutation procedure that we pushed what used to be at m plus first place. We took all the edges that started at the m plus first vertex and ended at the m plus second vertex. We pushed them into this jth place. So now they start at the j plus first vertex and end at the j plus second vertex. And then everything else we pushed by one step to the right. Okay, so this is the graph we obtained here. And now we are going to argue that we did not decrease the number of paths of length k involving a shifted edge. And then the second step would be to prove it for paths not involving any shifted edge. So let's assume that we have a shifted edge that participates in a path, It's part of a path of length k. And if a shifted edge were the first edge of x1 different paths of length k minus 1, x2 different paths of length k minus 2, and so on and so forth, until xm plus 1 of different paths of length k minus m plus 1. Mind you, it makes sense because this number is non-negative, right? M is at most k minus 1, k minus 1 plus 1 is k, k minus k is 0. So yes, it makes sense to speak about paths of length 0, because, well, there's just one such path. Well, actually here, sorry, I'm talking about a shifted edge being the first edge of a certain path. Well, a shifted edge cannot be an edge of a path of length 0. So then xm plus 1 is simply equal to 0. Yeah, but this makes sense. I'm just trying to tell you that the notation makes sense even in the extreme cases like m equal k minus 1. But it cannot be k, then it wouldn't make sense. We don't discuss paths of negative length, not until we get to the extended graphs and have the adjoint in our operator algebras. Okay, so then with this notation for x's, okay, we can count the amount of paths that involved the shifted edge that we lost. So we pick up a shifted edge and we count the number of paths of length k that involved this shifted edge and then we lost in our procedure. Okay, so of course we didn't lose any paths of length k that start with this shifted edge, because the shifting doesn't do anything to such paths, but because we detached this, we moved a shifted edge, says it used to start here at m plus 1 and started m plus 2. Then when we look at all paths of length k minus 1 that have our shifted edge as the first edge, well, then we lost the number of edges here times the number of these paths. So this is am. Okay, we lost am times x1 paths of length k, and then we look at paths of length k having the shifted edge, our chosen shifted edge as the third edge, and then we lost am minus 1 times am times x2 of such paths, and so on and so forth, until finally we can say that when we look at our shifted edge as the m plus first edge of a path of length k, well, then we lost a1 times a2 up to am times xm of such different paths. And look, here it's important that m is strictly less than k, because I'm telling you that our shifted edge is the m plus first edge of a path of length k. So m must be strictly smaller than k, but we have it. Yeah. So these are all the paths we lost that involve a given shifted edge, and that's the number. It's a concrete number L. But look at what we gained, right? But due to this eroding procedure, we gained. Well, actually, when we were looking at this number L, then we should have been looking at this picture, right? We moved, say, this is our shifted edge, so we move it there, right? So what we lose am time paths of length k minus 1 involving this edge as the first edge. We lose it because we cut it here. Then when we consider it as the second edge, when we lose am minus 1 times am times the number of paths of length k minus 2, having this as the first edge, and so on and so forth, right? So this L, this computation of L, is justified by the previous picture. Now, when I want to look at the amount of paths we gained, then this is given by this number G. And look what happens. Say that this is our shifted edge, this one. It used to start here, but now it starts there. Again, we don't have to count the amount of paths of length k having a shifted edge as the first edge, because this is unchanged completely by this procedure. So we are looking at these paths of length k having this edge as a later edge in this path. So the second, the third, and so on, right? So when we have it as the second edge, well, then we take, remember that the number of paths of a given length starting with this shifted edge does not change in this procedure. So that's why x's in L are the same as x's in G. This is very important to understand. Yeah. But now when we look at the paths that we gained and which are paths of length k and having the shifted edge as the second edge, well, when we gained am times x1. Then when we look at the shifted edge as the third edge in our path of length k, then we gained am minus 1 times am times x2 of such different paths, right? So we take all these edges, we multiply the number of all these edges here by the number of all these edges there, and by the number of all paths of length k minus 2, having this as the first edge, which is denoted by x2. We gained them because, remember, this edge started somewhere else. So we could not connect these paths to this edge. Now we can because we shifted it further. That's why this is what I count with the gain. And we continue like this until the index j plus 1. Right here, the numbers are basically changed. We look at the shifted edge as being an appropriate edge in a path of length k, and this is preceded by a path going from the vertex j plus 1 to the vertex m plus 2. And the amount of all such paths we gain is, of course, aj plus 1 times aj plus 2 up to am times xm minus j. Okay? And note that when I look at these m minus j terms, then they are exactly the same in G as they are in L. These are the same numbers, identical. But now things begin to change, right? So the first m minus j terms of L are the same as in G. Now we look at the next j terms in L. So now remember that before j plus 1, we have m plus 1 because of our cyclic permutation. So we continue counting the paths that we gained, but now we multiplied by different numbers than before. Now here, instead of aj, we have am plus 1, and so on and so forth. Then we'll have we'll have here aj, am plus 1. Instead of, as in L, we had aj minus 1, aj, and so on and so forth, until we arrive at a2 times a3 times am plus 1 times aj plus 1 up to m times xm, right? So when you look at these terms and you compare them with the last j terms here, as we argued before, we multiply a bunch of natural numbers and we replace each number in the set of natural numbers that we multiply by a number which is at least as big as this number. So then, of course, the product is at least as big as the product we had before. Because if every factor of the product we replace by a number which is greater or equal to this number, then we obtain a product which is greater or equal to the product we had before. So this note that the next string terms are no bigger in L than they are in G. Okay. And note that we have this one more term here, the last term, which definitely does not appear in L. In L, we have just m terms, but here we have m plus 1 many terms. And this is for the situation when L is strictly bigger than k plus 1. We already argued that if L is equal to to k plus 1, right? Wait a second, is it L or no, M? Sorry. No. We already argued that if M is the biggest number strictly smaller than k, which is k minus 1, then m plus 1 is just the path of length 0. And there are 0 paths of length 0 having the shifted edge as its first edge, because the path of length 0 has no edges. So then this term vanishes. If m is equal to k minus 1, then this term vanishes. And you can see why. Because if m is equal to k minus 1, then you cannot involve this shifted edge. Because if m is equal to k minus 1, already this path here, this bolded one, is path of length k. So when we start from the first vertex and go all the way to k minus 1 plus 1 to the kth vertex, then that's it. This is already path of k1. It cannot be followed by any path which contains an edge. So that's why this number is 0. But if m is strictly less than k minus 1, then yes, this term appears here. For instance, if m is equal to k minus 2, then this is a path of length k minus 1, and basically we can follow it by this edge. So then this is just equal to this x is equal to 1. xm plus 1 for m equal k minus 2 is equal to 1. Because there is only one path of length 1 involving the shifted edge as its first edge. It's the edge itself. Okay, and so on and so forth. So this term is generically non-zero, but in the special case of which is allowed in our reasoning of m equal to k minus 1, this term vanishes. But we are still good because first m minus j terms are equal. The remaining, the further j terms are greater or equal, and then we have a term which is positive, which is non-negative. It might be 0, but it cannot be negative, right? These are all natural numbers. So we are good. We gained more than we lost. That's exactly what we wanted. Yeah, and here's this discussion. Note that the last term is 0 for m equal k minus 1. This is what we explained. So thus, we have shown that applying this E2 to E3 to E4 to Fn procedure, we have not decreased the amount of paths of length k involving a shifted edge. So now we still have to argue about paths of length k not involving any shifted edge. And this is what we do in the next step. So let me now highlight it. We've got it. So let's consider the paths not involving any shifted edge. But this is much as we already argued before. When we consider paths not involving any shifted edge, we can just dump these shifted edges and consider sort of subgraphs without these shifted edges. So then this move of reattaching a shifted edge, shifting the edge, is irrelevant because we are not looking at a paths that involve any shifted edge. So we can forget this first part of the move, and the only thing that we care about is this permutation. Okay? But this is much as argued before, but this rearrangement procedure does not change the amount of all such paths. I mean, such meaning not involving any shifted edge of any given length if we start off at S of EM2 or further. That's because the rearrangement happens earlier. So if you look at paths that start further down the road, then obviously they are unaffected by this rearrangement. So we don't change the amount of all different paths of any given length. Now, we don't change the amount of all such paths of length k starting at the first vertex. Why? Because when we start from the first vertex and remembering that m is strictly less than k, if we have a path of length k, we must involve all vertices that are in the first part of a graph. Right? We must involve all of them. Because remember that m is at most k minus 1. So this is at most k. So if I have a path of length k, it must involve all steps that are bolded here. And since we involve all steps, such a rearrangement doesn't matter. Because if I have a product of elements and when I apply any permutation to this product of elements, because multiplication of natural number is commutative, I end up with the same product. Okay, and when I count the paths of length k that start at the first edge, I just have to multiply all these numbers, and then multiplied by the number of all paths of length, I don't know, k minus m plus 1, starting at m plus 2, but now not involving a shifted edge. So this is constant because this number is unaffected, and here, well, this number is affected, but well, it is not affected because the multiplication is commutative. If you want, the combinatorics is different because these changes make an effect on these paths, but they do not change the count. The number is still the same, okay? And finally, we look at all such paths starting the vertices 2, 3, 4, up to m plus 1, right? 2, 3, j plus 1, up to m plus 1. If you look at such paths, well, then again, it's much as argued before. We have to have the product of all these numbers to take simply all paths of appropriate length starting from 2 and ending at m plus 2. And then we multiply it by the number of all paths, which is unchanged, of appropriate length, having the shifted there are no shifted vertices. Sorry, we have no shifted vertices, and we look at all paths of an appropriate length, complementing to k the length that we have on the left, that start at s of em plus 2. This number is unchanged by this rearrangement, it's constant. And here, what happens with this rearrangement is, again, that we have a product where we replace factors of the products by numbers that are at least as big as the original number. So the product does not decrease. It might increase, but it definitely does not decrease. So this is exactly what is written here. And does not decrease the amount of all such paths of length k, starting at the vertices 2, 3, up to m plus 1. Well, now to finish the reasoning, it remains to apply this permutation algorithm E4 to EM to FM, which again, much by the same reasoning as before, I'm not going to repeat it, does not introduce a loop and does not decrease the amount of paths of length k. Remember, we had this, maybe I'll go back to it. This was this reasoning here, right? I'm not shifting any edges. I'm just looking at edges that are at the first part of my longest path, and I apply the permutation, which makes these numbers numbering the amount of edges emitted by a given vertex and on decreasing sequence. Yeah, so this is the procedure that I still have to apply to finish the algorithm. So when I say applying this algorithm E4 to EM, right? I mean, when I want to complete this algorithm E2, E3, E4, FM, remember that the last part is this E4 to FM, which means that I cannot just stop at the cyclic permutation, because it might happen, unlike in this picture, it might happen that here there is no jumping edge, and it might happen that m plus 2 is now much bigger than a1. So then I have to make an appropriate permutation. So that until I get the first jumping vertex, or I get to the last vertex, because we remember we might also get to the case when m is finally equal to k, and we are done with this part of the algorithm. But until then, we have to look at all these edges of the first portion of a part where there are no jumping edges, and when we look at these numbers, we have to arrange them in a non-decreasing order. That's this final permutation algorithm of completing the step E2 to Fm. That's E4 to Fm permutation algorithm. But it works exactly the same way as before. Since it does not shift any edges, this is just, this is exactly, it's over and over again the same argument. So I'm not going to repeat it. I hope it's clear. If it's not clear, please ask. Okay, so now we are done. I showed you that we apply such an algorithm, E2, E3, E4, Fn. We don't change the number of edges, it's still n. We don't introduce any loops. And we do not decrease the number of all different paths of length k. And this was the most difficult part of the construction. This is sort of the most messy combinatorics. It will not be any more difficult now. Now, I want to convince you that now we bump into another wall, that things are not as rosy as you might think they are. Because remember, our path, our longest path is of length L, which is strictly bigger than K. And what I'm trying to tell you is that we cannot apply this algorithm beyond K. Why? Well, of course, we can iterate this algorithm. This is sort of goes by induction, because you see, when I end this E2 to Fm algorithm and M is strictly less than K, then I can still apply it the next time, because I'm at the starting situation of this algorithm. There is a jumping edge. I can shift it. Then I can make this cyclic permutation. And then, if need be, I can make this final permutation step until I arrive at another biggest number, less or equal than K, such that there are no jumping vertices up to this vertex with this new biggest number. So I can iterate it, but I can iterate it only until I bump into M equal K. Why? So imagine, so we can apply it for as long until we transform E2 into Fk. So Fk is defined as Fm, but now M is equal to K. So we are no longer under the assumption M is strictly less than K. So now, of course, the graph of K has no loops, has n edges, and has at least as many different paths of length K as E2. So far, so good. However, we cannot apply this procedure any further, and we still might have jumping edges farther down the road, because it might happen. It might happen that say L is, I don't know, K plus 5, and it might happen that AK plus 1 is strictly less than A1, and when swapping the edges, as we do in this procedure of shifting, we have a jumping edge, right? And which starts at the K plus first vertex. So our procedure would be to shift its beginning one step to the right, and then make the cyclic permutation, making AK plus 1 first, then A1 second, and so on and so forth. But because, well, if we take such a situation that A1 is strictly bigger than AK plus 1, then swapping the edges, starting with the first vertex, with the edges starting at the K plus first vertex, this cyclic permutation, this will decrease, it will strictly decrease the amount of paths of length K beginning at the first vertex. Because before this permutation, right, and here, yeah, before this permutation, we had A1 times A2 up to AK, of course, different paths of length K, starting at the first vertex. But after we make this permutation, we have AK plus 1 many edges emitted by the first vertex, A1 emitted by the second vertex, and finally AK minus 1 emitted by the kth vertex. Now I can take this A1 through AK minus 1 is a positive number on both sides. I can divide by it. So this inequality is tantamount to saying that AK is strictly bigger than AK plus 1. But remember that we already assumed that A1 is strictly bigger than AK plus 1. So we arrive at the situation that oh, sorry, something is wrong. I divide. So here I have AK left when I divide, and here I have AK plus 1 left when I divide. Yes, fine. But okay, but you know that by construction AK is greater than equal than A1, because up to AK this is a non-decreasing sequence of numbers. So AK is greater than equal than A1, and A1 is strictly bigger than AK plus 1. So it means that AK is strictly bigger than AK plus 1, and that's this inequality that we have here. Multiply it by 2 identical positive numbers, and this is the equality. So we cannot make this move anymore, because we can have a situation, I'm not saying that it must happen, but it might happen. We might have a situation in which our procedure will decrease the amount of paths of length k. So the E2 to FM algorithm is not valid beyond k. So we might end up with a graph as in here. So now imagine m is equal to k. Imagine m is equal to k. So the first, the kth part of a graph is already what we want it to be. There are no jumping edges. Okay, but what happens beyond k is beyond the reach of this E2 to FM algorithm, and here there might be a mess. We might have jumping edges, whatnots. All right, but we can no longer apply our algorithm E2 to FM. Is this clear? This is just an example of what might go wrong. I mean, I'm not saying that it must go wrong, but it might go wrong. And in our reasoning, we must make sure that no matter what the circumstances are, the algorithm is applicable. We have this big quantifier for all graphs such that, yeah. But we can imagine the graphs for which things go wrong with this algorithm if m is equal to k. So we cannot go in general. We cannot go with this algorithm beyond k. So we have to force the situation to be such that we can apply this algorithm again. So now we're in the game of making the move which strictly decreases the number of vertices. And this is a very beautiful and straightforward move when you think about it. This is a very natural thing to do. I remember I saw at Sunny Buffalo a plaque on the wall saying, if an opportunity doesn't knock, build a door. So this is exactly what we are doing, right? We are building the door so that an opportunity can knock. we are devising a different algorithm to make sure that the previous algorithm can apply again. And to be honest, I like it a lot. So what do? You see it on this picture. We identify the first vertex with the k plus first vertex and shift all edges from the first vertex to the second vertex to become edges from the k plus first vertex to the k plus second vertex. Okay, so this is exactly the situation. We chop off all these edges on the left and we put them beyond AK, like in this picture. Okay. And we call the thus obtained new graph GL minus 1. A GL minus 1 because our longest path used to be of length L, and our longest path is of length L minus 1. So this stands for the length of a longest path. Well, clearly we introduce no loops. And better still, we have at least as many different paths of length k in this graph GL minus 1 as we had in FK. Well, let's check it. If we look at paths of length k not involving any shifted edge, then nothing changes. If I remove from fk this first part of fk, so all edges from the first to the second vertex and the first vertex, if I remove it here in fk, and if in gl-1 I remove these edges going from the k plus first to the k plus second vertex, then these identical graphs. So this means that there are exactly as many paths of length k not involving any shifted edge in fk as we have in gl-1, because these are identical graphs when we remove shifted edges. Okay, so this is the first part of the statement. And when I look at all paths of length k involving a shifted edge, then look, all such edges which are lost by our move are now reincarnated as paths of length k, starting at the first vertex in gl-1 and ending with the same shifted edge. So before we had to have a shifted edge here, which was followed by edges over there. But now, and this gave us a path of length k, but now we choose the same path of length k going from here to there. And now an edge which used to be the first one is now the last one. But of course, we didn't lose any paths. Before we had a1 times a2 times ak paths, and now we have a2 times a3 times ak times a1 many paths of length k that involve a shifted edge. So the number is the same. Any path which was lost due to this procedure was now reincarnated with an edge which was first becoming an edge which is last. Okay, I hope this is clear. So we are done. We can claim that in gl-1 we have at least we have at least as many different paths of length k as we had before. We might have more because it might happen that now we have some new opportunities with these new shifted edges being the first edges, and then we can take paths of length k-1 starting at this vertex here. But I don't know what L is, so it might happen, it might not happen. We don't care if we increase the number of paths. So what we care is that we do not decrease it. So that move I like because it's easy to explain. And now you see we have two tools at hand. We have this E to F algorithm, and then we have also this F to G algorithm. So next we repeat the above algorithm of reducing the number of vertices for as long as there are no jumping edges between the first k+1 vertices and the number of vertices is bigger than k+1. So if L is equal to k+1, then we are done, because right, if L is equal to k+1, it means that that's the last edge. So since we know by assumption that there are no jumping edges starting at the first vertex, second, and the k vertex, and the last vertex is the vertex k plus 2, because if L is equal to k+1, then we have k+2 many vertices. Well, but we cannot have any jumping edge, because the first jump, the jumping edge can only begin at the k plus first vertex. But for this to be a jumping edge, there must be at least k plus second vertex. Otherwise, it cannot jump over the k plus second vertex. Right. So if L is equal to k+1, we are done. There are no jumping edges anymore. So we have a path of length k+1, but no jumping edges. Well, actually, yeah, it's if okay, let me highlight it to have it. done properly. So what are we saying here is that we are we repeat this the above algorithm for as long as there are no jumping edges between the first k plus 1 vertices. Okay, and the number of vertices is bigger than k plus 1. Well, actually, I don't understand why. Because this last algorithm, we can still repeat if L is equal to k plus 1. So maybe there should be, well, we know that it's bigger than k. Maybe this part of the sentence is redundant. You see, because if you look at this move of shifting A1, of shifting these A1 many edges from the beginning to the k plus first place, well, we can do it even if there are no more jumping edges. Well, imagine that L is equal to exactly k plus 1, then we can still do this procedure. When we have a path of length k plus 1 with no jumping edges, but nothing can prevent us with taking these A1 edges and joining them to the edges we already have between the k plus first and k plus second vertex. This procedure still works. And the same argument works as we had before. So I think this part here is redundant. I don't have to say that the number of vertices is bigger than k plus 1. Yeah, I think the procedure still works. And in fact, in an example which I prepared for you, we are going to apply it. Okay, so if we, so let's ignore it. If we encounter jumping edges between the first k plus 1 many vertices, so if it happens, I have to go back again to this picture. If the situation is like in here, right? That we have no jumping edges up to k, but when we go to k plus 1, we already have a jumping edge, right? It might happen. But when it does happen, note that we can apply again this procedure E2 to EM. We build a door for an opportunity to knock. Because now we are in a situation when we have a jumping edge at a place M, which is strictly less than k minus 1, than k, right? Because we took away these first A1 many vertex edges, and we put them after AK. So now any path from here to there is only of length k minus 1. So if you have a jumping edge, our E2 to M procedure applies, because then M is simply equal to k minus 1, which is allowed. So that's the idea. Okay. And this is what we are saying. If we encounter jumping edges between the first k plus 1 many vertices, then we apply again the add E2 to FK algorithm. Of course, they can be only between k and k plus 1, k vertex and k plus first vertex, right? Because before, by assumption, we don't have any jumping edges. But we might have a jumping edge which starts at the k vertex, jumps over k plus 1 to k plus 2, stuff like this. Okay. So this F, yeah, and we can apply this E to FK algorithm. And when we applied, well, again, we end up in a situation when we can apply again, this time F to G algorithm, because the feature of the FK graph is precisely that there are no jumping edges starting at the first, second, up to the k vertex. There are no jumping edges. This is what this E2 to FM procedure guarantees. We arrive at the graph FK, yeah, which is the graph as in here, but for m equal to k. This is what this E2 to Fk procedure guarantees. But now we can again apply this F to G procedure. And because this F to G procedure reduces, at least it reduces by 1 the number of vertices in our path, our L is getting smaller and smaller. We first get to GL minus 1, then GL minus 2, and so on and so forth. At a certain moment, we must hit K, right? So in this way, we intertwine the application of the E to F and F to G algorithms until we arrive at the graph GK of a desired form. Then we have a graph with no jumping edges whatsoever, and which has a longest path of length K. And now it's really down the hill. Now we basically arrived at the parking lot. We can just relax and find the best parking spot. Because the last part is baby combinatorics, which is elementary. And I mean, not that this is not elementary, but it's just very involved and complicated. So the last step is to have this optimal permutation, optimal redistribution of edges among vertices so that we maximize the product. And this is exactly along the lines of one of the problems which I believe Jacek solved on the blackboard. So the final step, so now let me undo this highlighting. The final step is to prove that we can evenly redistribute, or let me highlight it, sorry. So the final step is to prove that we can evenly redistribute the edges, increasing the number of paths of length k to the bound P and K. And this is a primary school-like calculation. If there are any two indices, A different from J, such that BI minus BJ is strictly bigger than 1, so if the number of edges emitted from one vertex differs by more than 1 from the number of edges emitted from another vertex, we have to apply a corrective algorithm, okay? Then we define the prime numbers, so B prime mu is exactly the same as B mu when mu is not I and not J. Then B mu prime is B mu minus 1 for mu equal to 1. And B prime mu is B mu plus 1 for mu equal to J. So that's exactly this Robin Hood-like algorithm. We take from the rich and give it to the poor, but only to the extent at which the rich will not become poorer than the poor. That's important. So you must be richer, BI must be richer than BJ by at least 2. Otherwise, we don't do anything. Well, when we do this, we can now compute the product. What is the product of all? Oh, darn, there should be mu here. I forgot to change. I have the 2 places at which I forgot to change the indices. This n and this n is mu. I decided not to use n because n has a meaning in this theorem, so it might be confusing. That's why I went Greek. Okay, so what is the product over all mu's from 1 to k of B mu prime? Well, when mu is an index that is not I and j, then B mu prime is just equal to B mu. So that's this product. But then we have to multiply it by B prime I and by B prime j. But B prime I is BI minus 1, and B prime j is BJ plus 1. So when you multiply it out, we get BI times BJ plus BI minus BJ minus 1. All right? But now when I take this product where the indices BI and BJ are missing, and I multiply it by BI and BJ, I get back the original product. Remember, multiplication is commutative for natural numbers. And what remains is this product with 2 indices missing and multiplied by BI minus BJ minus 1. But by our assumption that BI minus BJ is strictly bigger than 1, this is a positive number. This is a strictly positive number. This is also a strictly positive number. So a number by a strictly positive number is bigger than this number. So this way we proved that the product of all primed b's is strictly bigger than the product of all unprimed b's. Okay, so this is elementary. This is not even high school. This is primary school. And of course, this way we arrive, we can repeat this procedure until there is no pair of indices, no pair of different indices with the property that bi minus bj is bigger than 1. Right? There are finitely many indices with finite differences. So at the end of the day, when we persistently apply this procedure, at a certain moment, there will be no pair of different indices with this property, because we keep on leveling things up. So at a certain moment, we will be done. And then we arrive at a graph with new pairs of consecutive vertices joined by b plus 1 and k minus new pairs joined by b edges. Right? At the end of the day, we'll just have two numbers, b plus 1 and b. Let me just highlight it as I want. Okay, so when we end this Robin Hood procedure, we will have we'll have a graph where we have new pairs of vertices joined by b plus 1. Of course, then we can make permutations in such a way that it does not affect the number of paths of length k. Remember that when we are already in this situation, it's obvious that any permutation whatsoever of these b's will not make any change in the number of all paths of length k. Right? This is pretty clear, because each time we have a path of length k, we must step on all steps. So by just making any permutation doesn't change the number of all paths. The multiplication, again, the natural numbers is commutative. So when we'll have new parts where we have b plus 1 many edges, we'll have new pairs of consecutive vertices joined by b plus 1 many edges, and k minus new joined by b edges, and we can arrange them so that they are or actually we don't have to arrange them. The combinatorics is the same. No, sorry, I think we don't have to make any rearrangements. We simply have a number of pairs joined by b plus 1 many vertices and a number of pairs joined by b vertices, right? And of course, the number of all such pairs must be equal to k. So if we have new pairs joined by b plus 1 many edges, then we must have k minus new pairs joined by b edges. So now we can compute the number of all paths of length k. This will be nu times b plus 1 plus k minus nu times b. When you multiply it out, nu times b will cancel out, and we'll end up just with nu plus kb. And of course, sorry. This is not the number of. This is the number of edges. Sorry, this is not the number of paths. This is the number of edges. Right? We have new pairs with b plus 1 many edges, so the amount of such edges is nu times b plus 1, and we have k minus new pairs joined by b edges. So there are k minus nu times b edges, and these are all edges that we have in a graph, so they must add up to n. So we have that nu plus kb is equal to n. And here we have to consider two cases. Of course, nu is non-negative because it's a number. It can be 0, but it cannot be negative. And we have, of course, I knew the biggest possible mu is k, because you cannot have, we don't have more pairs of vertices than k. There are just k different pairs of vertices, because this is a path of length k. The longest path is of length k. Okay, But wait a second, I think I made, yeah, sorry. So here there should be strictly less than k. Sorry, here there should be strictly less than k. This is a typo. And when mu is strictly less than k, and when you look at this equation, then mu is simply the rest, and b is our lowercase n, right? Because this is the decomposition of n into the rest, which remains from the division by k, and k times the number that you get by the biggest natural number, such as this number plus k plus a number smaller than k gives n, right? This is uniquely determined. So then we have mu equal to r and b equal to n. Otherwise, if mu is equal to k, which is also allowed, it should be just a separate case. This should be a sharp inequality. If mu is equal to k, well, then it's obvious that n is divisible by k. And if n is divisible by k, then the rest is equal to 0. And n, the result of this division is, of course, b plus 1. So consequently, the number of all paths of length k, of course, as it must be, is b plus 1 to mu times b to k minus mu. That's just by the definition of b and mu. But now we see what these numbers become in our two cases of interest. So if mu is from 0 to k minus 1, right? Then what we have, mu is equal to r and b is equal to n. So you have n plus 1 to r, all right? And we have n to k minus r. That's exactly the recipe, the definition of p and k. And what happens in this special case when mu is equal to k and r is equal to 0? When r is equal to 0, this term vanishes. I mean, it's just equal to 1. Now we have n is equal to so mu is equal to okay, r is equal to 0, all right, and n is equal to b plus 1. But yeah, sorry, I should be looking here, right? I should be looking here. Okay, so I want to see that these two numbers are equal in this case. So if so, what happens when mu is equal to k? When mu is equal to k, then this part vanishes here, and we have just b plus 1 to k. But b plus 1 is n. So we have just n to the power k on the left-hand side. And what happens here? R is equal to 0, so this vanishes. R is equal to 0, and we're left with n equal to k. So this equality holds. Lowercase n to k equals lowercase n to k, because this is what it is if k divides n. All right, so we are done. We proved that in this graph, by this Robin Hood procedure, we strictly increase the number of paths of length k to obtain the bound. Because the graph now with this distribution of edges between consecutive vertices has the property that the number of all paths of length k is exactly the number of a theorem, the P and K. So we constructed the graph which achieves this bound. And this is the final punchline, which I really like. Let me see if I can highlight it. Yes. So as an arbitrary graph, which we started from E, satisfying the assumptions of the theorem, can be transformed without decreasing the amount of all paths of length k. So we still have an edges, we still have no loops, and we make all these complicated algorithms. We consider so many different possibilities in cases. But at the end of the day, whatever we do, we still all the time talk about graphs satisfying the assumptions of the theorem. So we have n edges and no loops. And what is most important and most difficult is that in the algorithm we apply, the procedures that we concoct, we do not decrease ever the amount of all different paths of length k. All right? So this means that if I take any graph whatsoever, satisfying the assumptions of a theorem, it cannot have more than p and k different paths of length k, because I can transform it by an algorithm do not decreasing the amount, that does not decrease the amount of different paths of length k, to a graph which has exactly p and k many paths of length k, which proves that this is a bound for all graphs. And this bound is achieved by the reasoning above. So we conclude the proof of a theorem. Wow, perfect. We still have 21 minutes and the theorem is done, which means that we can still do the example. Now, do you have any questions? This was quite a long proof. Now, let me make, before we go into an example, which I think very nicely illustrates everything we do in this theorem. This is what I like about this stuff. It's so tangible. You can always imagine it. Let me mention the following. This graph theoretical theorem has a natural generalization in linear algebra. And when you generalize it, you sort of replace these natural numbers over here by positive numbers, positive real numbers. And you can phrase this theorem in terms of matrices. And you can actually prove this theorem. And when you prove this more general theorem, when natural numbers are replaced by positive real numbers, then this theorem now has a shorter conceptual proof claimed by Alex Kirvasitu. It's a recent paper on the archive. I looked it up, but basically what he does, he has some short proof of a generalized theorem which recasts this theorem in terms of linear algebra. It's no longer a graph theoretic proof. It's no longer a combinatorial proof, okay? But now, of course, it's more general, it's shorter, so you can say that it's win-win. But I really want you to see a purely combinatorial graph algebraic proof of a graph theorem. It's sort of like the fundamental theorem of algebra, right? This is a fundamental theorem of algebra, that every polynomial with complex coefficients has a solution. It's a very beautiful, important theorem. But all elementary proofs of this theorem are not algebraic. I mean, typically you use analysis to do it, right? So it's kind of funny that you use analysis to prove a fundamental theorem of algebra. But now I remember that one day I found somewhere a purely algebraic proof, non-analytic, purely algebraic proof of the fundamental theorem of algebra. But if I remember correctly, this was a very heavy Galois theory. This was very complicated proof. So it's sort of a similar situation here. Our proof is complicated because we're using simple tools. But I think it's worthwhile for the understanding of what's going on. This is a very direct hands-on combinatorics that proves a very, well, non-trivial statement. No matter how much you simplify the proof, this will never be a trivial proof. And of course, if you have any idea how to simplify this purely combinatorial graph theoretic proof without using any non-combinatorial, non-graph theoretical tools, please let me know. I'll be very interested to know if we can simplify it, because 6 pages is quite long, but at least all moves, as complicated as they are elementary. This is just elementary hands-on combinatorics. It's just complicated. Okay, so if you have no questions concerning the proof, and I think it's a beautiful problem for a written exam. Prove the theorem, 15 minutes to write an answer. Just kidding. Okay, let's do, there is no written exam. Let's see how it happens, what happens in an example. It was not so easy to devise this example because I wanted to have an example in which all moves that we are doing in the theorem are somehow non-trivial. So I wanted to make it as small as possible to make my life easier, but somehow the simplest graph I could come up with, I did it together with my PhD student Mariusz, the simplest graph we could come up with had 16 edges, and we were considering paths of length 3. Okay, so this is our graph E. It is right here on the picture, right? So I'm looking at the number P16, 3, so I'm counting all paths of length 3 in this graph. And it's very easy to count that you have just 6 of such paths. Right, there are absolutely no paths of length k in the right-hand side part of the graph. The longest path here is of length 2. And when you look here, the only paths of length 3 that are in this part of the graph must start either here in this vertex or in that vertex. If you look at any other vertex, there are no paths of length 3 starting at such a vertex. So we can use only these 2 vertices. So at the end of the day, it's obvious that we have 3 edges times 2 edges times 1 edge. That's 6. Okay. So look, if you start with a generic messy graph, it has actually very few paths of a given length. Right? We have 16 edges to play with. It looks like a lot. But we chose a random graph, and then we have only 6 paths of length 3. So now we apply our algorithm. So remember, first thing that we do is that we relate the unrelated vertices. So Oscar, here's an answer to your question. I did it in a certain way, but this is by no means unique. So look what I did. It's a pity that I jumped pages here, because it should be great to see these 2 things at the same time. So first, these 2 indices are unrelated, so I joined them. Next, these 2 vertices are unrelated, so I joined them. Then these 2 vertices are unrelated, so I joined them. Then these 2 vertices are unrelated, so I joined them. And then finally, these 2 vertices are unrelated, so I joined them. Okay? And then I arrive at such a graph. I hope I didn't skip any step. And this graph, remember, was called E1. And now again, we can compute. The length of the longest path is still 6, right? But now the number of all different paths of length 3 drastically increased. We jumped from 6 to 31. Okay, we can just do it step by step. The situation is sufficiently simple that you can just do it by hand by looking at all vertices and counting how many paths of a given of length 3 they emit. There is a smarter way to do it. What I'm going to do later on in the lecture course is to define adjacency matrices. I'm going to define an adjacency matrix. And by the way, this is exactly by the adjacency matrix that you get generalized, that you go to linear algebra from graph theory. It's very simple to compute. Given a graph, you can write down a matrix. Then you raise this matrix to the kth power. I mean, so here k is equal to 3. So you have a given matrix with natural entries and natural number entries, and then you raise it to the 3rd power. That's not a big deal. And then you add up all entries of this matrix. Just add them up. And then this is the number of all paths of length k, of length 3 in this case. All right. But here we can very easily do it by hand. Okay, you can just count. So how many paths of length 3 we have starting at this edge, and you count. Here you have 4 times 2 times 1, or 4 times 1 times 2. So this is messy. I mean, of course you can do it, but it would take, it's boring and take a long time, right? So let me skip it. You can just trust me that it's 31. We have only 12 minutes left, and I want to finish this example, and it goes until the end of the page. So let's not overdo it. You can have it as an exercise, count it without the help of adjacency matrices that indeed here have 31 different paths of length 3. Okay, but now we transform our graph from E1 to E2, which means what? Which means that we take care of this jumping edge. There's only one jumping edge starting at the first vertex. And remember that what we do here, we shift the beginning of this jumping edge so that this jumping edge is no longer jumping. So this means that we shift the beginning of the jumping edge to be the third vertex. Okay? And when I do it, this part remains the same. That part remains the same. I just, flipped the edges and introduced additional notation. But basically what happens is that here now we have two edges, right? Because this edge that used to start here now starts in the third vertex. So here now I have two edges from the third to the fourth vertex. Here I remain with 4 edges. Here with 2 edges, I have a jumping edge over here, right? And here I have 2 edges, and this part is unchanged. This is just a different notation. Okay, now again, we can compute the number of all paths of length 3 in this graph, and when we compute it, we see that it's 43. Is already these graphs are getting simpler and simpler, so it's easier and easier to multiply it and compute it by hand. But I have only 10 minutes. I don't want to do it. Again, you can just do it as an exercise and see what happens when we go from E2 to E3. Right. So this means that now, okay, and remember, as I told you, it might have. I have something here. Chat. Okay, Alex. Okay, Alex just signed out, and he was kind enough to inform me. It might happen that here there is no jumping vertex. So then automatically, if there is no jumping vertex, then automatically E2 is E3. The procedure of going to E2 to E3 is just identity, right? We do nothing, but here in this example, this is how it was cooked up. In this example, we have a jumping edge starting at the second vertex. So the E2 to E3 procedure is non-trivial. Well, we just shift the beginning of the jumping edge from the second to the third vertex. So now we have 4, 2, 3. And we are already lucky because 3 is our K, right? So now, now we have this procedure. Sorry, this E3, sorry, E3 to E4 procedure means that if I have this number bigger, sorry, this number, sorry, if I have this number smaller than that number, then I have to swap them. Right, this is this procedure going from E3 to E4. So we already removed the jumping edge, right? But now we look at these two numbers and remember that we have this permutation that if A1 is strictly bigger than A2, then we swap these two pairs of vertices together with the attached edges. So now instead of 4, 2, 3, we have 2, 4, 3. And that's V4. And now already it's okay. So going to E3, we have 47 vertices. And now making this permutation, we actually again gain it. We have 59 vertices. Not vertices, different paths of length 3. Okay. Why can't I scroll? What happened? Why? Right, so here it happens that after applying this E3 to E4 procedure, we don't have any jumping edge starting at the third vertex, and our biggest m that we consider in the algorithm is actually equal to k equals to 3. And this E4 to Fm algorithm means simply that when we look at all these initial k pairs of, which means three pairs of vertices of this graph, we have to choose a permutation such that these numbers in parentheses going from left to right form a non-decreasing sequence. Yeah, so this is this step. 2 for 3 is no good because 4 is strictly bigger than 3. So there is an obvious permutation which just swaps these two guys and keeps the first one unchanged. And now we have 2, 3, 4. And even such an innocuous move increases the number of paths by 3. You can just check it. Here is actually very easy to check it. The graph is already sufficiently easy to check how many paths of length 3 you have. And lo and behold, when you make this permutation, you increase by 3 the number of different paths of length 3. Okay, so now this is our Fk, or if you want F3, and we cannot apply any longer this E to F algorithm. Now we have to apply this F to G algorithm. So now we will decrease the length of a longest path from 6 to 5. This is our GL minus 1, and L was 6. So now we have G5. And now we are looking at all paths of length 3 in this new diagram. And remember the procedure, we take all these edges and we shift them from here to start in there. So now we have 3, 4. Here there was just one edge, but we had 2, so this becomes 3. Okay, so this is the way we obtain the graph G5. But now, because we have a jumping edge starting at the third vertex, this procedure E to F is again applicable. So we can apply it again. And remember what this procedure does. This procedure first shifts all jumping edges. There's just one. So we shift this jumping edge now to begin at this vertex. That's the first move we make. And this is this right-hand side part of the graph involving the last 3 vertices, right? It's the same as this one, only now this jumping edge starts at the 4th edge, vertex, which means here. Okay, but now we also have this 3, 4, 3. But remember this swapping procedure. Now we have to exchange 3 and 4. So we end up with 3, 3, 4. And so this is like our E4 stage. And to get to Fn, we would still have to permute all these numbers if need be. But because they are already in non-decreasing order, this E4 to Fm part of the procedure is identity. We do nothing. Because the swap itself, the E3 to E4 step, already makes things in a correct order. That these AIs are in non-decreasing, form a non-decreasing sequence. Okay, and here actually, well, it's not computed, but I can assure you that if you compute it, it will be not less than 90. This is very easy to compute. You can do it. I have only 3 minutes, so let me make sure that I finish on time for a change. But now you see, we are again in the position to apply this F to G procedure. But what is this F to G procedure? I gave the first 3 edges and I shift them from here to begin at this edge. So now I have 3, 4 to begin with. And now here, instead of 1 edge, I have 4 edges because I shifted 3 edges over here, right? So now our graph is getting simpler and simpler. Again, it's very easy to compute the number of all paths of length k, of length 3 in such a graph, and it's 116. Now, the longest path in our graph is of length 4, so this is why now it's designated G4. And now we still have to apply the procedure E to F and then F to G to arrive at G3, okay? So what is this procedure? First, we shift all jumping edges, starting at the third vertex. We move their beginnings to the fourth vertex. So then a diagram we'll have no jumping edges whatsoever, and the number of emitted edges will be respectively 3, 4, 4, and 5. Because now these 3 edges will start in here. So it'll be 3, 4, 4, and 5. Okay. Now, according to this E to F procedure, we should make a swap, but here the numbers are in very good order, so there's no swap. Then another thing you think about is all right, but now we have 3, 4, 4, 5, and what we do is we don't have to make a swap because everything is in the right order, and we also don't have to make any of this permutation that makes these numbers turns the sequence into that makes sure that this sequence of numbers is non-decreasing. We don't have to do it because it's already non-decreasing. This algorithm is just identity in this case. And we are in a situation in which, as I said, we had 3, 4, 4, 5. Yeah. So that's the end. This E to F procedure in this case is just shifting these jumping edges, because all these permutation parts, E3 to E4 and E4 to FM, is trivial. It doesn't have to be applied because things are already in a non-decreasing order. Okay, but we still have a longest path of length 4. So the F to G procedure applies. So from 3, 4, 4, 5 graphs, we get now 4, 4, 8 graphs, because we shifted these 3 edges to begin at this edge. And then we already had 5 edges, we added 3, so we have 8 edges. And now we are home and dry, because we finally have a graph G3 with no jumping edges, and with all and with a maximal, the longest path of length 3. Okay, so now it's obvious that the amount of all paths of length 3 is just 4 times 4 times 8, which happens to be 128. And we have oops, in the remaining -1 minute, we have the last final step to make, which is this redistribution. If we apply this optimal redistribution algorithm, this Robin Hood algorithm, we change 4, 4, 8 into 5, 5, 6. And when you do it, it's obviously the amount of all paths of length 3 in this graph is 25 times 6, which is 150. And this is exactly what is given to you by the theorem, right? Because 16 decomposes as 5 times 3 plus 1. So P16(3) is exactly 5 plus 1, this is n plus 1, to r is 1, so it's 6 to 1, and you have n, which is 5, to k minus r, which is 3 minus 1, so it's 5 squared. So 6 times 5 times 5, exactly as in here, is 150. So this ends the example and ends our class for today. And I'm really happy because I did almost exactly on time everything I wanted to do. If you have any questions, fire at will. If not, I think we are all sufficiently tired to call it a day and meet in a week. So are there any questions? Okay, if not, thank you very much for your patience. I strongly recommend that you have a look at the lecture notes on the Moodle page. Just use this link, it's all the time active, because it's this kind of a proof which is easier to read than to listen to. I think you will be better off understanding what's going on by reading what I wrote than by listening to my mumbling. Still, I think it might be helpful to fill in some gaps and plant some ideas in your mind. Okay, so thank you very much for your patience, and till next week. Bye-bye.
Okay, bye-bye.
Bye-bye.
Bye.
Bye.
Bye.